In general, to analyze convection problems, we do need to know what the flow does. And so here we're going to consider perhaps the simplest type of problem, which is a laminar pipe flow. So it's sometimes called an internal flow, as we've discussed before, and it's laminar, and laminar meaning that molecular diffusion is the process by which mixing occurs. So the assumption here is that we have an initially plug flow of fluid that enters a pipe or tube. And in the initial section of this, there's the development process that occurs. And so here we're going to focus on what is sometimes called hydrodynamically fully developed flow. And this is going to be different from what is going to happen when we look at the heat transfer problem, and we're going to then look at thermally fully developed flow. So the development process in the hydrodynamic entry length problem is the process by which the velocity starts off as this plug flow. So imagine a situation where the velocity comes in flat at 1 meter per second. And we know that the no-slip condition on the wall forces the velocity to immediately go to 0 meters per second at the wall. To conserve mass, or the mass flow rate to be equal at the inlet at any point downstream, means that there's actually an acceleration in the core. So whatever the velocity had been, it has to have increased within what is often called the potential core to make up for the fact that it's being retarded in some layer near the wall. And you can think about that layer as a boundary layer of sorts. So it's retarded near the wall and accelerating off the wall. And so you see that the flat profile, so there's a region where the wall influences the flow, and I guess in some sense it influences it everywhere because of the acceleration, but there's a place where it retards the flow. That region gets smaller and smaller until at some point there's no longer a change in the profile as we go downstream. So in the momentum or hydrodynamic problem, the point of being fully developed means that the velocity profile no longer changes downstream. That is, du dx is equal to 0. Now, just to give some sense to why this is occurring, it's worthwhile, and how it occurs, it's worthwhile thinking a little bit about our point about the diffusion processes and diffusion scales. So imagine that we're following a chunk of fluid. So this is not an Eulerian, and now we're looking at this in a Lagrangian sense. So we put a chunk of fluid, it's more complicated than that, into the system, and as it goes downstream, and we're going to look at this sort of the velocity. So as we go downstream, we have, and again, increased penetration of the influence of the wall. So away from the wall, the velocity is something, but near the wall, it's 0. As we continue to follow this in sort of this simple sense, there's increased penetration of the influence of that wall region until we get to some point downstream where it's penetrated the whole way into the system. Now, you can think about the distance over which this penetrates, the impact of the wall penetrates, in terms of delta, which we might consider some sort of diffusion length scale. So there's some region over which diffusion matters, and that diffusion affects the evolution of the flow. We talked about diffusion in conduction as the process by which the boundary condition influences the temperatures inside. And we said that it looked like the square root of the thermal diffusivity times the time. And so there's a very similar relationship in the momentum problem that's dependent on the kinematic viscosity times the characteristic time. So for the momentum problem, the parameter of importance, nu, is the kinematic viscosity with units of meters squared per second. So this is what affects the ability, this molecular processes of diffusion into the system. So really what we're asking at what point to be fully developed might mean that delta looks like d over 2. So it has to penetrate all the way in. And rather than talking about this in time, it's worthwhile thinking about this time variable as some length scale x over some effective velocity inside that system, u. So if we simply substitute these parameters in, we get d over 2 looks like the square root of nu x over u, again some characteristic velocity. And if we square that, we get d squared over 4 looks like nu x over u. Okay, so now it's worthwhile saying when, this particular x is the fully developed length. So when that delta is equal to d over 2, that x that we're talking about, that downstream distance, is the fully developed length. So we define the, we multiply both sides by u, so we get u d, and just hold on a second as far as this is concerned. So we get u d over nu looks like, and I'm going to delete the 1/4 over here actually, looks like xfd over d. So it says, in some sense, the fully developed length divided by the diameter should look like something multiplied by the Reynolds number based upon d. So remember that RED is a characteristic velocity d over the kinematic viscosity. And so correlations show that in the laminar range, the fully developed length divided by the diameter is about 0.05 Reynolds number based upon d. Remember that laminar conditions hold when the Reynolds number is less than about 2300.